Hi, it's time for another math easy solution. Turn to discuss further into applications of integrals, and now look at an example of the cardiac output video that I went over in my last video. And basically, just a refresher, this is an image from my last video, and I showed that when you have so the veins here, the way the body, the cardiovascular system works, you have oxygen depleted blood from the body goes through the veins up to the right atrium, which gets shipped through the pulmonary arteries up to the lungs. So it goes to the lungs, and then from the lungs it goes to the pulmonary veins, so this one and this right here, and then it goes into the left atrium, which then goes into the aorta, which is like a main artery, and those arteries are just going to be taking this oxygen filled blood, because the lungs is what fills the blood with oxygen, and then it goes to the rest of the body, etc., and it keeps going in a loop like that. So it goes from the body to the veins down here, and then it goes back here. So it goes, it's a kind of a big loop like that. Anyway, so example I'm going to go over is stated here, a 5 milligram bolus of dye. Bolus is just just a fancy word for a lump of whatever, any substance, or a pill or a drug or whatnot. I don't know, my calculus book uses this word. Anyway, so if a 5 milligram bolus of dye is injected into the right atrium, that's over here, the concentration of the dye in milligrams per liter is measured in the aorta, as I explained in my last video, using the dilution method. So this atrium right here goes to the lungs, and then back into the left atrium, and then back into the aorta. So if we put the dye in here, and then the concentration of the dye is measured in the aorta. So we add a dye there, and we add a probe here, and we measure the concentration, and it's a function of time. So we'll call it measure the concentration, which is function of time right here. Is measured in the aorta at 1 second interval. So basically measuring it at every second, as shown in this chart here. So let's say these are the measurement readings for whatever probe that you have in there. So at t equals 0, the concentration is 0. We haven't done anything because we just inserted the dye in here, so the blood hasn't traveled to the aorta yet. So obviously the concentration is going to be 0. After a second, you're going to have this much, 0.4, then 2.8 after this, and then the highest concentration is around 4 seconds, 9.8, and then you're obviously going to see it dissipate as it goes to the rest of the body. And then finally, after 10 seconds, we have a 0. So the curve looks like this right here. Every second, it's measured the concentration there. And now the example states, it's to estimate the cardiac input, or in other words, the rate of blood flow, the volume rate of blood flow that the heart is pumping. And again, I went over the formula for this in my last video. So recall that I showed that the blood flow, or the flow of blood, or the flow rate, or cardiac input, so many ways of saying it, it's going to be F equals to A, which is the amount of the dye. So, and then it's going to be the integral from 0, in our case 10 seconds, C of t dt, which is the concentration, of the dye. And again, it's in milligrams per liter right here, times in seconds, so that's C of t. So, I'll just write that down, where A equals amount of dye that we're injecting into the right atrium. In our case, this equals to 5 milligrams. Let's write this meter. And again, F is equal to, right here, equals to the flow rate, which is the same as the cardiac input, or output. Cardiac output. So now we know that A is 5, we just have to solve this integral right here. But since we aren't given a function, this is more of these are just data points we're measuring, we can approximate this integral right here. And if we look here, and also in my earlier videos on approximation, I showed that you could approximate this using Simpsons rule. So let's write recall Simpsons rule approximation, because all we're trying to do is find Simpsons rule approximation for integrals. In this case, we're just trying to find the integral right here, which can be viewed as the area. And again, the Simpsons rule, like I showed in my earlier video, it uses parabolas to estimate it, and it needs to be even number of intervals. So in here we have 10 seconds. That's 10 intervals right there. Yeah, so that is even number. So what we do is it's a 3-point system like this. So after every 3 points we get an estimation like this, and then so we draw a parabola after every 3 points and you apply the Simpsons rule. And again, this makes more sense when you watch my earlier video on the Simpsons rule, and I have the video link below. So what we're basically doing is estimating it using parabolas every 3 points. 0, this is 1, 2, and from 2, 3, 4. So this one is going to be these are all parabola estimations. Parabola estimation using Simpsons rule. And again, the formula for that, as I explained in my earlier video, so we're going to be approximating this integral 0 to 10 of ct dt, and this roughly equals to delta t over 3. So again, this is the Simpsons rule approximation, and then we're going to do, this is going to be c of 0, or t1, plus this is going to be 4 c of 1 after 1 second, plus 2 c of 2, then plus 4 c of 3, and then we follow the same pattern over and over again, etc., blah blah blah, like that. And then it goes from 4, then 2, then 4, then 2, etc., all the way. Let's go to the last bit, which is going to be plus, I'll just write these whole things out actually, just to make it easier. So 4c3 plus 2c4 plus 4 concentration at 5 plus 2 concentration at 6 plus 4 concentration at 7 and plus 2 concentration at 8. So just tedious to approximate, but it's pretty straightforward. C9, and then the last one is going to be the same as similar to the first one, just plus c of 10. So there's no coefficient in front. And again, it follows from the 4, 2, 4, 2, 4, 2 all the way, and then we have 1 at the ends and beginning. And again, make sure to watch my earlier video on Simpsons rule to get up to date on that. So when we approximated this roughly equals to, when you plug in the numbers, our delta t is simply 1 because it's every 1 second we're calculating here. So the delta t is equal to 1 second. So I'll just write that down. So 1 over 3, write this neater. So c of 0, let's go up here. So we have 0, 0, then 0.4, 2.8, etc. So we have 0 plus 4, 2.8, plus 2, let's see what this was. Actually, whoops, it's not 2.8, it's 0.4. Then 2.8. Let's go back up here again. Yeah, 0.4, 2.8, then 6.5, 9.8, 8.9. So this is going to be 4, 6.5, and then plus 2, 9.8, then plus 4, I think it was 8.9. And then it goes to plus 2, 6.1. Let's do it by memory. Then plus 4, 6.0, and then plus 2, which is going to be 2.3. Then plus 4, the last one, 1.1, and then plus, this is going to be just by itself, 0. And again, let's go back to double check. So 0, 1.1, so 0, 1.1, 2.3, 4.0, 6.1. There he is, 1.1, 2.3, 6.0. Yeah, this is the only thing wrong actually. This is not 6.0, it's 4.0, and then 6.1. see that again. So 4.0, 6.1, 8.9, etc. Again, it's just tedious stuff. 4.0s. So yeah, if I made a mistake, just type it in the comments below. Yeah, now when we plug this into the calculator, as I've done here, so 1/3, then plus 4 times 0.4, plus 2 times 2.8, etc. Go all the way over here, we should get an answer, I guess, 41.8, and I'll round up to 7. So we get, this is going to be, I'll just write this down, the integral from 0 to 10 of C of t, the concentration, or the area underneath the concentration curve, is roughly equal to 41.87, and this was in units of, well, it's going to be concentration milligram over liter times it by the time unit, which is seconds, like that. So now to get the cardiac output, we'll just solve that formula. So F equals to A over integral from 0 to 10 of C of t dt, which roughly equals to 5 milligrams divided by, then plug in this number, 41.87, use the units milligram per liter, times by second. So the milligrams cancels, the liters goes on top, and we're going to have a flow rate of whatever liters per second. So this equals to, yeah, let's just get to this. I wrote it down right here, 5 divided by 41.7. I didn't use the significant figures and all this, just wanted to round it up anyway. So just it doesn't need to be too accurate because we're estimating anyway. So this is going to be 0.119, or I'll round up to 0.12. So this is about 0.12, and again, liters per second. And to make more sense, I will multiply this by, well, 60 seconds over 1 minute. So this is the ratio of seconds to minutes, so we want to get this in terms of minutes. So when we do this, and again, I'm not using significant figures, I'm just going to go 0.12 times 60 to get another approximation. So 7.2 liters. So the final cardiac input is going to be roughly equal to, this is going to be 7.2 liters per minute. And a more sensible number in terms of minutes, easier to understand. So this is about almost 2 milk jugs of blood. It goes through that your heart pumps every minute, which is quite amazing. Anyways, that is all for today. Yeah, hopefully you'll learn from this pretty interesting example on using Simpsons Rule approximation. It just gets a better approximation. You could use any other approximation, it won't be as accurate. You could use a right endpoint, middle, center or midpoint approximation, etc., as I went over in my earlier videos. But Simpsons Rule is the most accurate in most cases. Anyways, that's all for today. Hopefully you'll learn. Like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.